I will now talk about another algorithmic technique that is very powerful and important for solving problems. It's known as dynamic programming. Okay, dynamic programming, or DP for the acronym. Dynamic programming has nothing to do with the programming as the way we know it, about writing code and so on. Dynamic programming is about recursive reasoning and recursive algorithms. So in dynamic programming, we reason about the problem recursively, or in a divide and conquer way. We come up with a recursive algorithm, but we have a smarter implementation of the most straightforward dynamic recursive algorithm that you come up with. Okay, so first we think about the problem recursively. How do we solve a problem in terms of solutions to sub-problems? Then we need to think about how do we implement it more efficiently than through recursive implementation, when possible. Okay, so not every problem is amenable to dynamic programming solution. And I will illustrate dynamic programming through a sequence of the examples. They come from different domains and illustrate dynamic programming in different ways. I will start with the simplest, which to me is the simplest example of dynamic programming that is usually not shown in textbooks, but it's about a very important formula that we have seen in 182. And this is the formula for the binomial coefficient. So I remind you that the binomial coefficient is the n choose k. Okay, so the number of subsets of size k from a set of size n. This is also the coefficient in the expansion of x plus y to the power n. Okay, and we know a formula for this. N choose k is n factorial divided by k factorial times n minus k factorial. So one simple algorithm for computing n choose k. So we want to write an algorithm that takes as input two parameters n and k and computes n choose k. So one simple algorithm is, okay, first compute n factorial. So write a loop to multiply 1 times 2 times 3 all the way to n. Then compute k factorial, compute n minus k factorial, and do the division. This is, of course, a simple algorithm. It's a few lines of code. The issue with that algorithm is that it has a lot of multiplications and then it has a division at the end. These are expensive operations. Multiplication and division are expensive, especially for n and k being very large. Okay, now this is expensive and we would like to come up with an algorithm that, for example, avoids multiplication and division. In this case, we would like to use summation. How do we use summation to compute n choose k? Again, in Comp 182, we talked about one identity, one of the identities for binomial coefficients that's very powerful for computing n choose k. And it comes from recursive reasoning, actually. Because think about it, that you want to count the number of subsets of size k from a set of size n. Well, how do we form a subset of size k from a set of size n? One way is to designate an element in that set n and say, I don't want it to be part of my subset, which means I need to take now the k elements from the remaining n minus 1 elements. So it's n minus 1 choose k. Or that element that I designated, I say it is part of the subset, therefore I need to choose k minus 1 remaining element from the n minus 1 remaining element in the big set. So it's a plus n minus 1, choose k minus 1. Okay, so this is one of the identities, and this is known as Pascal's identity for the binomial coefficient. Now, if you look at this is a recursive formula for n choose k, and using this formula, we can easily write a recursive algorithm in a couple of lines, right? So I can, for example, if I want to write a recursive algorithm, recursive n choose k, that takes n and k as input, and always we assume that always k is smaller than or equal to n. Okay, it makes no sense to choose 15 elements from a set that has 3 elements only when we choose without replacement. Okay, so always assume k is smaller than or equal to n. So I want to write this. Now the recursive formula, of course, I can now call the function recursively n choose k on n minus 1 k, and I can do recursively as well n choose k on n minus 1, k minus 1, we can return this, right? Now, we have always to think about the boundary cases, because what happens when, for example, we cannot just keep dropping and decreasing n and decreasing k. We cannot go to negative numbers and so on. So, for example, we can add the boundary case that if n and k are the same, or k is 0, how many ways you can choose 0 elements from a set of size n, or how many ways you can choose k elements from a set of size k? It's 1. So you can return 1 here. Return 1, else we return the sum of these two recursive calls. Okay, so this is a simple recursive algorithm, 4 lines. Okay, if I count the if and else on 2 different lines. Okay, so this is 4 lines. What's wrong with this? It's going to be doing summations, right? I mean, it's going to be recursively summing, and so on. Let us illustrate what would happen when we run this algorithm. Please keep in mind that, again, for n, in every call, in the next 2 calls, the n decreases, and in one of the calls, k stays the same. One of the calls, k decreases by 1. Okay, so think about it that we will make 2 recursive calls. The n will always decrease in both of them by 1, and the k in one of them is going to remain the same, in one of them will decrease. Okay, so imagine I want to call this algorithm on, I want to compute 8, choose 4. Okay, so if I want to call it on 8, choose 4, again, remember that n is going to drop in both cases. So this is going to make 2 recursive calls, one on 7, and the k doesn't change, and one on 7, and the k changes as well, right? So if you call the function recursively on 8, 4, it will be calling the function recursively on 7, 4 and 7, 3. The 7, 4 is going to be also on 6, 4 and 6, 3. And this one here is going to be on 6, 3 and 6, 2. This one here is going to be called on 5, 4 and 5, 3. This one is going to be on 5, 3 and 5, 2. This one is going to be on 5, 3 and 5, 2. This one here is going to be on 5, 2 and 5, 1. And this is going to, now I'm not going to write the whole tree here, but this is going to be now on 4, 4, 4, 3, and this is 4, 3, 4, 2, 4, 3, 4, 2, and so on. Okay, so this is a tree that shows the recursive calls. We start at the root of the tree. We are going to call the function on 8, 4. It's going to call the function twice recursively on 7, 4, 7, 3. These 2 recursive calls are going to result in 4 calls, and then these 4 are going to be in 8, and then 16, and so on. Now, if you look at this, one of the things that you will notice if you look at it carefully, and I'm going to color it now with, let's say, red here. Look at this, and look at this here. When the recursive call comes and evaluates 6, choose 3, is going now, this recursive call is going to blow up and compute this entire tree here. Okay, this entire tree is going to be computed now. Okay, now when the recursive call comes to evaluate 6, choose 3 here on the right, is going to go through the same subtree here and calculate it again. So what the recursive algorithm, that recursive algorithm we just wrote, this recursive algorithm is not smart in the sense that it had already calculated 6, choose 3. Why isn't computing it again? Okay, now if you look down the tree, you'll see the same problem. Actually, it explodes in different places. So this is 5, choose 3. This is 5, choose 3. This is 5, choose 3. The recursive algorithm doesn't know, the way we wrote it, it doesn't know that these values have been computed already, and I should not be computing it again. Right. So the recursive algorithm is going to be doing the same amount of work over and over and over. If you implement this algorithm, take n to be 1000 and k to be 20 and try to run it. Don't wait in front of the computer, because this is an exponential algorithm. It's going to result in an exponential amount of time, and 1000 choose 20 is not going to be a good number to look at. okay, and to deal with. So this is your first, for most of you who haven't seen dynamic programming, I hope you see the rationale behind the need for dynamic programming is that I have a recursive algorithm, looks very nice. The pseudocode is 3-4 lines. The implementation is also 3-4 lines. However, this kind of algorithm, implementing it like this, will lead to unnecessary amount of duplicated work that shouldn't have been done. And this is where dynamic programming comes into the picture. Dynamic programming says, when you come to 6, choose 3, and you compute this value here, store it somewhere, okay? And next time you come to evaluate this 6, choose 3, check in that table or in that array where you are storing values and see, has 6, choose 3 been computed? If it is computed, then just choose the value from that array, which is O of 1 operation, because all I need to do is just look up in that table where I'm storing the values. If it's been computed and the value is 2000, I just take 2000 and I don't need to evaluate this entire subtree here. Now we kill this subtree. So you will immediately see that we gain so much by getting rid of this kind of duplicated calculations with that simple trick of storing values in a table or in an array. Now, dynamic programming algorithms that you will see always have this issue of either we store the values in an array or in a matrix and so on. However, don't take dynamic programming as an exercise in filling tables and arrays. Always think about dynamic programming as follows. First, think about the problem recursively. What do I mean by recursively? It's divide and conquer. Divide the problem into smaller sub-problems. So in this case here, I want to compute 8, choose 4. I divided it into 2 sub-problems, 7, choose 4, and 7, choose 3. Now, if the 7, choose 4, and 7, choose 3 do not overlap, they do not have anything in common, then I cannot do much about it, right? And recursive implementation is going to be fine. However, since 7, choose 4, and 7, choose 3 have an overlap, then let's compute that overlap once and make use of it when we need it, okay? So dynamic programming is first think about the problem in divide and conquer, which is again recursively in our case. And the second point is reason about these solutions, find where the overlap in the sub-problems is, and think about how you can store this overlap such that you can calculate the values efficiently. So if you think about this, the recursive algorithm went from the root of the tree down to the leaves, right? So the call started at the root of the tree. It made the call to the 2 children of that root, went all the way to the leaves of this tree. For us to compute values in a non-redundant way and store them, now dynamic programming is actually going to go the other way around. It's going to go from the leaves all the way to the root. So let's actually compute the smallest values. We store them, and when we want to compute the next n choose k or I choose j, we first look up the table to see if I choose j has been computed. If it is, just take the value from there. Otherwise, just move on, right, to calculate it. So if I want to think about dynamic programming, n choose k of n and k, so think about it now. I want to actually, let's say, I want to have something like this here. So imagine that this is k here, and this is where the n. So I want to compute the values from, this is 0, 1, 2, all the way to k, and this is 0, 1, 2, all the way to n. Suppose I have this table, and this table, let's call it A. I want this entry ij here, this aij, to store the value I choose j, okay? If I build this table, then if I build this table here, then if you look at this value here, which is the n, the row n and column k, then this is, based on the definition of this matrix, is going to be the n choose k, okay? Now, how do we build this table? I want to get to this value at the end. And again, remember that the k cannot be larger than n. okay, or the j cannot be larger than I. So we are going to be calculating values on the diagonal and whatever is under the diagonal here. Okay, these are the areas that we're going to be calculating values. Okay, so the first thing we can do is we know the value in this column here, right? So this, we can initialize this. What's the, if you think about it, I choose 0 for whatever I is, it is always 1. So we can actually fill this table with 1 here. These are all 1. Okay, and then we can proceed. So I can now go to this value here, compute it. Then I can go to these two values, compute them, and so on. Okay, so if I want to write this dynamic programming, I would say that let's first fill this first column here, which says for I equals 0 to n, we will basically say AI 0 is 1. Okay, so I choose 0 is 1, no matter what I is. Then from that point on, I can go now from the second row, from the second row here, sorry, from the second row, which is I equal 1 to n, and the k again cannot go, the j cannot be greater than I, so we can go for j equal 1 to I. So this is the j. How do we calculate this? Is aij, based on the formula, it is a I minus 1 j plus a I minus 1 j minus 1. And this is the, and then at the end, we can say return a n k. Okay, so this is the dynamic programming implementation of this. So if you think about it and go back to that recursion tree, you will see that we are building the tree from the leaves all the way to the root, because when we filled first AI0, we went all the way to the leaves. That's where the in something choose 0 is. Then we go to one layer up, which is something choose 1, and then we go another layer up, something choose 2, and so on. So if you think about this algorithm, this now computes that n choose k, but what's the running time of this algorithm? If we think about this algorithm here, this is O of n, right? It is just n iterations. And this one here is n iterations. This, in the worst case, is going to be n iterations. Look at what happens here. This is where the main calculation happens. We don't calculate anything recursively. We put the values in the matrix. So this operation of give me AI minus 1j and give me AI minus 1j minus 1, these are one operations. So this end up being, this whole thing end up being O of n squared. Okay, so we had the recursive algorithm and we have dynamic programming algorithm. We went from exponential running time for the recursive to quadratic. Okay, the reasoning is the same reasoning, right? I mean, if you look at this line here, aij, what I put in entry ij in the matrix, this came from Pascal's identity, which is a recursive formula for that. However, after I looked at the recursive formula and after I evaluated that recursion and I looked at the recursion tree, I saw so much overlap, so much computation is being done over and over and over. Then I need to think about, okay, I need to, once I compute a value, I need to store it. Next time I need it, I need to make use of it. Okay, and this is what we did here. We dropped all the way from exponential running time to polynomial time, and not just polynomial, it's quadratic, right? So if you take here 1000 choose 20, this is going to be very, very efficient. Okay, so this is in the order of million operations. That's nothing on today's computers. The other one is going to be on the order of thousands to the 1000 to the 20, and that's not good. Okay, so this is the main idea of dynamic programming. We think about the problem recursively. We come up with that main recursive formula that n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. And that's where the reasoning starts. Okay, what is it that, where do the subproblems overlap? How do I store them? How do I store them? and in what order I need to compute them. Okay, in what order I need to compute them. For example, to compute I choose J, I should have computed already the I minus 1 J and the I minus 1 J minus 1, right? Because I need to make use of these values.